Hello, ladies and gentlemen. Warmly welcome to our live webinar here at EMAG Lasertec in Heubach. And we are very proud to present you today our webinar to the theme brake disc production from the turning process over LND to grinding process. My name is Martin Abenschein. I'm at EMAG in Saarlach, the technical application team manager and mainly responsible for the brake disc turning process. And together with me here is Dominik Grimminger and Yannick Röttger.
Thank you, Martin. Yes, my name is Dominik Grimminger. I'm the product manager for the coated brake disc at the EMAG Group, and I'm responsible for the complete process chain.
Good morning. My name is Yannick Röttger. I'm responsible for the Department of Grinding Technology at EMAG, now with a special focus on grinding of coated brake discs.
Okay, thank you. So before we start with our webinar, some organization points. You are very warmly welcome to send us your questions within the webinar, and to do so you have two possibilities. The first one is you can send directly in our comment chat so everybody can see your question, or if you would like to send us a personal question, you can also do this on the same menu, but by using the question button on the lower side of the menu. Then only we get this question and we will very pleased to answer your questions. So just to shorten the time, we will collect all the questions during the webinar and have a question and answer round at the end. So please feel free to send us all your questions. Thank you. And now I hand over to Dominik. He will start now with the invitation.
Thank you, Martin.
Welcome.
So I start with the brake disc itself and the Euro 7 norm. So the brake disc as a strategic part at the EMAG Group always has the starting process turning. So every brake disc has a pre-turning process. The traditional brake disc has mostly a finished turning process. So this way is the traditional brake disc. Some brake disc in the Asian market has a grinding process at the end, and especially for the European 7 norm, we have this hard coating of laser, so laser process, maybe a single layer or multi-layer, and as a finished process, again a grinding. We have some alternative process for the hard coating, but at the EMAG Group we focus on this path. So the turning, the laser coating and the grinding, and special for this webinar. Why we have the topic of the Euro 7 standard, the European Parliament has this new regulation, so to reduce the brake particle emissions from brake disc and tires especially, this means new cars are allowed only to produce or emission 7 milligram per 100 kilometers, and electric vehicles only 3 milligrams. Especially these small particles, smaller than a grain of sand. So a grain of sand has 90 microns, and the particle, whereas now in the Euro 7 standard are regulated, are 10 or smaller. So we have a compare here. This means particles with the size of 10 microns are collected in the throat, and particles smaller than 2.5 microns are collected in the lung or in the blood. So this is a huge health issue, and with the new Euro 7 standard and regulation, we want to avoid this issue. So we go through the single process steps, beginning with turning, laser coating and grinding, and Martin will start with the turning process.
Thank you, Dominik. Okay, so coming to the turning process, the normal way to produce a brake disc is that we start with the casting process So the brake discs, ventilated ones or solid ones, will be casted, and then after that we start with the machining process of these brake discs. So normally the brake discs come in gitter boxes or on pallets, and then has to be brought into the production process, either loaded manually by the operator to the in-feed conveyors or by a robot system. Then we do have the machining process itself, the turning process, the drilling process, or like Dominic explained before, for the Asian market also sometimes the grinding process for the cast iron brake discs is done. After that we have the follow-up processes like balancing, like measuring, like marking either by laser or by needle marking, and then at the end we have again the finished part handling by robot unit, or and directly transfer into the painting or coating units for the finishing then after that. If we now have a look in a production line as a reference with 4 setups, here in the beginning we do have the robot cell itself, so the robot takes the raw part and puts it onto the in-feed conveyor. Then we have 2 VSC 400 Duo machines for the machining process, so we have op 10 and 20 in the first machine, op 30 and 40 in the second machine. In between we have a gantry system which takes the part after OP10, flips it over by 180 degrees, brings it back to the machine. Then we are machining the second side, OP20, brings it out, and then the gantry takes the part and puts it onto the buffer band in front of OP30. Or if this is necessary and requested by our customers, we do have here also an SPC chute or an SPC drawer, so that you can easily take out the parts to measure them during the machine is running already with the next part, especially for setup, or if you have a tool change and you want to measure the first part after a tool change. Then in OP 30 and 40 we do have the follow-up processes like drilling and fine turning, and at the end again we have a gantry unit which is also flipping over the parts and brings the part at the end to the follow-up processes. So as you can see here, we do have a full modular concept. We have always the same machine type. We always use the same gantry loaders, so that we can really do it on a very cost-efficient way for a complete line. Then afterwards, in this example, we do have a balancing machine with 2 stations. The number of stations depends on the cycle time of the process. We can have a single, a duo, or also a trio station system for the balancing, as well as following up for the measuring unit and the marking units. Here we have one combined system for measuring and marking, but there could also be 2 different systems. And at the end of the line we do have again a robot unit which takes the finished parts and puts them here into gitter boxes on a conveyor system. And also here we do have the flexibility that we could also include some more units like a washing box or whatever is needed. So this is a general overview of such a line. And if we are now looking into the deeper process, we start with OP10. This is typically the clamping situation in the ventilation slots for the ventilated ones, or in the OD or on the head for the solid ones. And we are doing the rough cutting process and the finish cutting process or pre-finish cutting process for the clamping surface and the locating surface. Then in the second operation we are doing the second rough cutting process of the second side and already finished turning process of some areas. In this setup we have a special multiple drilling head for OP30 to do the drilling operation for the screw holes in one time, and also for the assembly holes with a multiple drilling head. And at the end we are doing the complete fine tuning process here by use of an NC straddle tool for the friction rings and with normal standard tools for the rest of the head and so on, that the geometry itself is based in one clamping. And this straddle tool can be mounted either on the sidewall of our VSC machine type or directly on the turret. So also here we do have the complete flexibility in the application. If we are talking about our machine types, we have two possibilities. The first one is the customized machine world. Here we are talking about customer specifications which we have to fulfill, special requirements which we have to fulfill, and here we are normally using our VSC machine types. Here we are talking about machines for the big OEMs or tier 1, tier 2 suppliers with special requirements and specifications. As you can see here, we have the VSC machine type in two possibilities. The first one is a single machine type with only one working area, or we do have our VSC duo machine type with two complete independent working areas. So you could have here simultaneous machining in both working areas the same, OP1010 for example, or you could have alternate ones, OP10 in the left one, OP20 in the right one. Both types are common that we do have our complete closed machine base and body made of mineralite. Why mineralite? Because mineralite has an 8 times better damping attitude than cast iron. And this is very important, especially if you have interrupted cuts during the process. Because of this, we have longer tool lifetimes and we can achieve better surface qualities and accuracies. And of course, we are using our hydrostatic guideways in the Z-axis in both types, because the dual machine is nothing else than a single machine put together with one control, with one E-cabinet, with one hydraulic unit, but splitted working areas. So they are completely independent from each other, so that the vibrations which are caused, for example, during the rough cutting process, will not be transferred to the other half, where you can do a finished process during the same time without any influences. Here you can see such a reference line consisting of 4 VSC 400 duo machines. Here each machine is doing simultaneous operation, OP1010, 2020, 3030, 4040. And afterwards we do have a measuring system, we do have a marking system and a balancing unit. This is a line especially for complete high mass production of car brake discs. On the other hand, if we are talking about standard machines, then we do have our VL and VM machine types, which of course can also fulfill customer specifications, but these are our standard machines out of our range of standard products, which starts from VL2 from diameter 100 mm up to VL8 with diameter up to 500 mm in clamping chuck size and with a rotation diameter of 520 mm. So especially the VL8 machine is suitable for brake discs up to 430, 440 mm and can completely combined also in a complete production line. If we are talking about a high flexible solution system, then we are talking about our VM9 BD machine. This machine is a spindle down machine. This is different to the VL8 or VSC machine types, where we do have the hanging spindle with the hanging clamping chuck. Here we do have a spindle down machine, and as you can see here, it's very easy to load the machine also by hand. Both machine types, of course, do also have a column made in mineralite for the best damping situations during the process. And here you can see a very flexible system, a very flexible solution, especially for the aftermarket, because here we have 3 VM9 machines positioned around one robot unit in the center, which is loading and unloading the machines with raw parts and take the finished parts out. And here we are doing the process in 3 operations. And this is, as I mentioned already, a high flexible solution, because if you have a very small lot size, but you need the parts very fast in a very, very short period of time, then you even can load these machines by hand. You can set up the machines very quickly, and you don't have to use the robot for that. If you have to make only 10 or 20 or 50 parts, you just load the machines here directly from the front door, because you have a complete accessibility to the machine itself, even if you have a robot system standing beside it. So you can use it as a single machine or in the combination as well. Okay, so that was a very short overview about the possibilities for the turning and drilling process. Of course, we do also have machines for the drilling operations, for the perforation drilling holes in the friction rings, or we have machines, combined machines for the turning and grinding of the cast iron brake discs. If you are interested in these applications as well, I warmly invite you to visit our homepage and there our media center, because there you can find a lot of webinars and also one of production of, let's say, classic brake discs made in cast iron, and of course also other applications which we did and which we make already a lot of webinars which you can visit there and find there. Okay, now I hand over again to Dominik.
Thank you, Martin.
You're welcome.
So we start with the laser cladding process. Here we have a slow motion video from our application center. Here you see the powder cone, so the powder gas mixture, and in the middle you see the laser beam. And for the process we have a melt pool right above the surface, so the process itself, it doesn't go directly on the cast iron, it's slightly above the process, the cast iron. When we talk about the process, we have to talk about the layer. So we have options for a single layer system. Single layer system means we don't have any buffer layer between the friction layer and the cast iron, mostly used for lighter vehicles. And the other 2 options are multi-layer systems. We have a bonding layer with a thickness around 100 microns to 150 microns. It's a stainless steel in most cases. And we have our friction layer. The friction layer is a combination from carbides and also stainless steel matrix. We have some versions with titanium carbides or titanium ferrochrome carbides. So that's one case, and the other one are with tungsten carbides. So different layer system, all proved with the laser cladding process. When you have a special powder or a different layer system, please let us know. We can prove and test our process with your powder in our laser application center. So these are crosscuts after the cladding process. We are here live from Heubach, so we have the opportunity to show the K-figures directly on the machine. So please follow me, I will show you the machine itself. So I'm standing here right in front of the ELC 452 LMD. You see we have here our process module. We have this modular system, which means we can choose different machine size, beginning with 1 process module. Here we have a machine with 2 process modules, or even the possibility to have 3 process modules. So depending on your layer system, depending on the layer's thickness and the production scenario you have, we will find the right machine concept for you, which fits for your needs perfectly. So the machine itself, from the left to the right side, we start with an automation module. There are 2 conveyor bands inside. who are responsible for the loading and unloading, so raw part and finished part. Right in front on the worker side, we have our powder feeder and powder hopper system. Here as an example from our technology partner, HPLV Codur. These powder hoppers are a little bit special because they have this top-down system. Here we have with the system the possibility to have a really fast refill or change of the material and the powder. So it means we can change each powder in less than 30 seconds. So with a fast system for you and for your production. The powder hoppers has a powder feed rate of 150 gram per minute. So for each hopper 150 gram. In this system we have our bonding layer here, our matrix here, and our carbides are in the last hopper. So with this system we can produce for each process module a bonding and a friction layer. Let's have a look inside the machine. Right in front we have our process optic, we have our melt pool monitoring, and at the back side we have our surface scanner. The clamping device is made by EMAG, so we have our special clamping device only for this process. To show you the process, we make a short clip, so have a look on. So here you see two ELC 452 LMD machines. We have the options for a manual loading and the option for automatic loading, so with a gantry or a robot cell. Inside of the machine we have our handling system, a gantry loader who is responsible for handle the parts for module 1 and module 2. On the first station we now have the application of the bonding layer, so the first layer system for both sides. Also the layer thickness sensor are for the in-process measuring. The gantry loader also are responsible for the flip over, so the whole system is responsible to handle the parts from the raw to the finished part side. Our table has a switch time of 0.8 seconds, so to minimize the powder loss and the idle time. Now we are on the application of the friction layer, and again our surface scanner are inside. The surface scanner is responsible because when you want to check your layer thickness, you have to cut the parts, and so you have a look on the process itself. Also included are our powder collector in the middle of both machines to avoid to spread over the powder into the machine. And you will receive a finished part at the end of both process or both process modules. So here on an example of the Frio machine, we have the integrated automation, so you are only responsible to handle the raw and the finished parts. We have the technology package inside, who includes also a quality software and the quality features. We have our angle on the table. Why we choose this angle? We choose this angle to avoid the process emission, to have flashback on the process optic and the nozzle to reduce the wear. And with our machine concept, you only have one central supply for the power, so you only need one central supply for dual, Frio or mono machines. The same as the automation interface, you have only one connection to your system. So I hand over to Yannick Röttger and the grinding process.
Thank you, Dominic. In the next chapter, I'd like to give you a short overview of the last process step, double-side face grinding. Why is it necessary to have a post-processing after laser cladding? Depending on the carbide size and the process parameter during laser cladding, the average surface roughness of the coated brake disc is up to 100 micron. For the functionality in the brake system, an average surface roughness of maximum 5 microns is required, for some applications even lower. Not only the microgeometry, the roughness makes it necessary to do post-processing because of the thermal impact, the energy impact during laser cladding. There is a relaxation from residual stresses which lead to shape deviations of the brake disc after the cladding process. You can see the topography after the coating for the brake system. After the grinding process, actual runouts of maximum 20 microns are required. Dominic already presented an overview of the coating systems which are produced in laser cladding. We, of course, do the grinding process for them. Very challenging for the grinding process because of the hard particles are the multi-layer technologies. The friction layer after cladding has an average value of 250 microns, and usually after the finishing there is a requirement of a thickness up to 100 microns. The problem is that every optimization in the laser cladding process, which lead to an improvement, to a reduction of the fine dust emissions in the brake contact, usually makes the grinding process much more challenging. Because here we want to remove in a short time a high material volume, and so that's a target conflict. What is our answer, the EMAG answer for this machining task? The VLC 450 DG. This machine is based on decades of experience in the construction and manufacturing of machine tools with vertical spindle layout. The customer or its automation system provides the raw part in a horizontal orientation on the workpiece shuttle. On the Q1 axis it goes into the machine. The raw part is lifted up by the V1 axis and provided to the main spindle S1 with the clamping device. The XI1 axis brings the part between the two double-side grinding wheels, and during production we have an actual infeed of the two grinding spindles S1 and S4. So this results in the grinding result with a cross pattern structure. The machine is designed to machine workpieces, brake discs with an outer diameter up to 450 millimeters, so we are already prepared for the production of brake discs for trucks. What are the main advantages of this machine concept? We have a very good accessibility for setup and maintenance work. The operator has a good overview of the contact zone between grinding wheel and brake disc. The grinding chips fall down in the dust collector and are removed out of the machine by the coolant. So especially the abrasive hard coating particles have a very reduced contact to the machine axis and their sealings, which has a positive influence on the reliability and the lifetime of this machine. The customer just has to provide the part in horizontal direction or take back the ground part from the workpiece shuttle. Everything else, clamping and so on, is done by the machine itself. Now you see some live pictures. In the background you see our laser cladding machine that Dominic just presented. Just opposite of it we have one of our 4 grinding machines for prototyping. Here we are producing prototypes for many different customers, for different coating systems, not only coating systems that have been produced here in Heubach, also cold gas spray coatings, whatever the market requires, we can grind it here in our shop floor for prototypes. To give you a better overview of the machine and its kinematics, we provided a video without coolant. Here you see that there is a good accessibility, a good overview. The workpiece shuttle brings the part into the machine. The workpiece lift gets the finished part after machining from the main spindle or provides the new part, the raw part, for the production. The one axis, it is brought in a grinding gap between the two grinding wheels, and now actual infeed takes place for the machining. For the coolant supply, we use needle nozzles. They are focused on the finish thickness of the brake disc, so they are always correct positioned. We do not need any wear compensation. For different brake disc geometries, for different thicknesses, you can change the whole system of the two needle nozzles to save time for tool and workpiece change. In the top view of the machine layout, you can see that we have a very small footprint. If you use a single unit for coolant supply and filtration, we have a footprint of 3.6 meters in width and 8.5 meters in length. It can be reduced if we do not need a single unit for filtration and coolant supply. If we need a central station, we have really a very small footprint. We need small space in your production, and as you can see, there's a good accessibility of the supply technology for maintenance. Our tool concept bases on small rings which are fixed on a spindle flange on the ground body. These rings have a weight of maximum 5 kilograms. The grinding layer, the abrasive layer, is put on this ring. It is very easy to change them. 10-minute tool change time for 2 spindles, so we have the possibility to save time in production and also to adjust, to choose the correct tool for the individual coating system, because every coating system requires its own designed grinding wheel specification. We're using diamond or CBN or mixture of both grain materials for our grinding layers. The average grind diameter varies between 126 and 251 microns depending on the application. We use the whole range of bonding systems for the grinding wheel. We achieve good results with metallic bonding, also with ceramic bonding, vitrified bonding, and for some applications we have good results with resin bonds. Main focus currently is on CBN and metallic or vitrified bonding. We work together with the leading manufacturers of grinding wheel in this branch. It is our job to enable them to make very good grinding tools who achieve good results with regards to low costs, high wear resistance, and good quality of the finished part, so the customer can choose his preferred supplier for the grinding wheels on whatever location he wants to produce brake discs. What makes the tool design and the selection of the right process parameters so difficult? We are dealing with a multi-phase material. What does it mean? We have two materials: the soft stainless steel matrix with a ductile machining behavior, and the hard coating particles with a brittle hard machining behavior. For ductile materials, you usually use high relative speeds, try to produce low chip thicknesses. For hard brittle materials, you use different grinding tools and low relative speeds to produce micro cracks which lead to the machining. As you can see here in the analysis of a cut brake disc, we have to be able to cut as well the soft matrix and the carbides. This makes it quite difficult to find the right setup. Currently we are working with in a range of grinding wheel circumferential speeds between 2 and 30 meters per hour, and our grinding spindle has to provide very high torque for this application. Besides the material properties of the brake disc, also its geometry makes the grinding process challenging. Of course, our dream case is a coated brake disc with a perfect flatness without any warping. It would be enough to have a total depth of cut during grinding which is just slightly higher than the surface roughness to get a grinding wheel, to get a brake disc according to the quality requirements. Real conditions, these are shown on the right side. Due to the thermal impact, we have a warping, we have shape deviations, so it is necessary to grind a higher depth of cut, a higher grinding allowance. If we choose too high feed rates, too hard grinding tools, which provokes high normal forces, then it is possible to get a clean surface, to get rid of the surface roughness. But as the brake disc is quite flexible in the actual direction, after the contact to the grinding wheels, the friction ring would flip back and we would have problems with the geometry, with the run out and the flatness of the finish part. If we try to avoid high normal forces, we can work with low feed rates, which lead to a high cycle time. We do not want to achieve this, or we use very sharp grinding wheels, which lead to a high tool wear. Then it would be possible to make parts with a good surface roughness and a good geometry. But as you can see in this case, the friction layer has a conic shape, so the material efficiency is very low because we have a constant friction layer thickness after coating, and in this area we have to grind much more material than necessary. So the key message of this slide is that it's very important to have a cross-process optimization with special regard to laser cladding and grinding process. Single optimization for both process steps would not lead to a good result for the customer. That's why we are very happy that we can analyze and optimize both processes here at EMAG on one facility. Finally, I want to give you a short overview about cycle times and results that we achieve if we have a perfect input quality after laser cladding for the grinding process. So it is just necessary to remove a very low grinding allowance. This, for example, for single layer technology, which is quite common in mid-range passenger cars, on the rear axle with an outer diameter of 300 millimeters, which leads to a friction ring surface of approximately 50,000 square millimeters. We can achieve a cutting time after after workpiece change and search for contact of about 1 minute. For higher dimensions, for example 356 millimeters, which refers to the friction ring surface of 80,000 square millimeters. We see these discs often with a coating with Titan carbide in 430L. We have to calculate with a cycle time about 1.5 minutes for perfect input quality. Or the biggest diameter in passenger cars, 420 millimeters with titanium carbide, ferrochrome and 316L. a friction ring size of 100,000 square millimeters. It leads to a cutting time of approximately 2 minutes. Very important to clarify that higher grinding allowance, of course, leads to higher cycle times and higher wear, and also important that there are some coating systems which are much more harder to machine, so it's important to find the best solution to every coating system. Every system has its own set of parameters which lead to the best results in production. Just some words to the achieved quality. The flatness is lower than 10 microns, surface finish lower than average surface roughness of 4 microns. The actual runout measured on 3 different slides lower than 20 microns, and the DTV, the thickness variation in circular and circumferential direction lower than 2 microns, and in radial direction lower than 10 microns. Finally, I kindly invite you to the Grinding Hub, the leading grinding technology exhibition in mid of May in Stuttgart. You can see our VLC 450 DG in real life. We will present our new concept for in-process measurement and the concept for data recording it in laser and grinding process. So we have a holistic system for the data transfer between both machines. We will present this here in May in Stuttgart, and you can also see our vertical grinding machine for external or internal circumferential grinding, and some machines for universal grinding. Would be a pleasure if we meet in Stuttgart. Thank you very much.
So now I will give you a quick overview over all 3 processes, how a production line can look like, made by eMAG. So all 3 processes are connected here. We start on the left side. We have our bin picking cell, so loading of the parts. We have the pre-turning in 4 operations, means 2 VSC 450 duo machines. Operation 1, 10 and 20. The gantry with the flip over function in the middle. Then we have OP 30 and 40, so drilling and finish turning on the second machine. After the turning operation, we need the marking and balancing and the end of line measuring as the traditional brake disc. After that, we have the conveyor system to our cladding machine. Here we have the link with gantry again. So we decide here for ELC 450 Frio machine, a 2-layer system, means we have the bonding layer in the first module and the friction layer in module 2 and 3. After cladding, we have a surface temperature between 100 and 250 degrees. Depending on the layer system and laser power we use. So after our cladding process, we go through a cooling tunnel on the back side, as we also use at our common laser welding process to have the parts again at room temperature to give the grinding operation the best starting parameters. Then we have 2 VLC 450 DG machines, so 2 times the grinding, also linked with the gantry system. And after the process is finished, we have our conveyor system for the finished part, linked to an end of line measuring system for the end control, and packaging cell, so again a robot cell. This is what a complete line can looks like. At the eMAG group we have different variations of automation systems, so we are more than happy when we can calculate and have a project with you to optimize this line for you and your needs. So we are done or finish with the presentation. Martin, maybe we have some questions
Yes.
to the webinar.
Okay, indeed we have. I think we got a lot of questions. So I think the first one is already for Yannick. Question is, what is the cycle time average for the grinding operation, and what is the true life of grinding wheel per parts?
Yeah, unfortunately, it's quite difficult to give a precise answer to this question because there are many influencing parameters on cycle time and, of course, the tool life. So we found some information about different coating layers and different friction ring sizes in the presentation. So there are many applications where we are working with cycle times lower than 2 minutes. But as it's absolutely based on the coating system, on the grinding allowance which is necessary to remove, and on the friction ring size, I kindly invite you to contact me together with my technical sales team. I'm sure we will find a good approximation for your individual machining task.
Okay, thank you, Yannick. Then the next question came up. I think it's one from my side, so I will answer that. In comparison, how much is the save between VSC and VL solutions? Can be in percent, and about quality, the same. Okay, let's start with the second part of the question. The quality is the same. It doesn't matter if you have a VSC machine type or is it a VL machine type or VM machine type. So it's not a question of the machine, it's a question of the application, what we want to do with the machine type and what is a special request for it. And for the question about the price or the cost savings, that's quite hard to say because, as I mentioned before, if you're talking about specifications, customer specifications, we are normally using the VSC machine type. And these machines, of course, with the pricing for the specifications, are then higher than the VL machine types. On the other hand, the VL machine type is our standard machine, which we are producing in a big lot size. So, of course, here there is a price difference, but we are not looking in the first step which machine we are using. We are looking in the application, and then we choose the right machine for the right application. Okay, next question. I think this is again for Yannick. How often is the dressing with tool material diamond? Just an example, please.
All our grinding wheels that we are using are pre-profiled and work in the self-sharpening conditions in the machine because the hard coating particles in the brake disc, they are our dressing tool. They lead to a certain amount of loads on the grinding wheel, which makes sure that we always get sharp grains into contact.
Okay. Then the next question, also again for you, Yannick, I'm sorry for that. Yeah.
These questions, we can discuss this in detail with some more information about your machining task. You got a good overview and a good approximation for the 3 different coating systems on the last slide, I think.
Okay, then the question for Dominic, what laser power can be used?
Machine or our concept is made from beginning 10, 12 kilowatts up to 20 or 24 kilowatt laser. Depending on your task, we choose the right laser power. But in this field, between 12 and 24, everything is possible.
Okay, then what powder consumption can be expected?
Powder consumption is not easy to explain. I can give you an example with a 16 kilowatt laser process. We have a powder consumption on the bonding layer of around 130 gram per minute. So this is a powder consumption as a example. Powder consumption is depending on your laser power and the brake disc itself. Maybe you have a case and we can calculate it for you. But as a approximation, 130 gram per minute on a 16 kilowatt laser process.
Next question. Do the components have to be cooled after coating? I think you explained it again.
Yes, components, when you mean the brake disc, yes, they have to be cooled because of the heat after the cladding process. So when you go into the machine with 250 degrees, it's not an option. And depending on your automation system, some parts will have 200 degrees, some parts they need a little bit more time in the automation. They have 120 degree, and so it's not an option for the grinding process to start one with 80 degrees and the other one with 40 degrees. So we have to be cooled. We have always need the same level on the part.
Okay, next question. Which cutting material do you use and what is your experience regarding the achievable tool life? Okay, so maybe I start with the first part for the turning process. So normally we are using ceramics or CBN or even sometimes only tungsten carbide. It always depends on the quality of the material and the storage time between the casting process and the turning process. If you're talking about a very good European casting material and process, especially in Germany, then we are talking about CBN. So we are already using CBN for the rough cutting process. But it's usual to use ceramics for the rough cutting and then CBN for the finish cutting process. And Yannick, from your side?
We use in most of our applications grinding layers with CBN grains because of this micro splittering effect. They provide a sharp grinding wheel topography, make sure that we cut the materials, but there are also applications where we achieve good results with diamond grains. So it depends on the coating system and the referring process parameters in laser quality. The tool life depends on the friction ring surface, on the coating specification, and on the grinding allowance. So difficult for us to give a general approximation.
Okay, one more question. Oh, I think this is one from my side. You show a multiple drilling head in OP30. Is this not a disadvantage in terms of flexibility? As I mentioned already during my presentation, it depends always on the request from our customers. If we are talking about a mass production request, so that we have to produce a lot of parts within a year, then it absolutely makes sense to use a multiple drilling head to make the drilling process in one step. On the other hand, if we are talking about a high flexible solution for many different kind of brake discs with different pitch diameters and even number of holes, then of course we also can use live tools on the turret to make it one by one. Okay, so I think this is the last question now. Okay, that's a good one. If the disc is perforated in the working area, when is then the drilling operation? I think this is now for the perforation on the friction rings. So from the conventional process, we are doing the perforation drilling process after the fine turning process. So first fine turning of the friction rings, and then we do have also special machines to make 3 holes, up to 3 holes at once in the machine by use of 3 milling spindles. And after that, this disc will also be transported to the LMP process. Dominic, correct me if I'm wrong.
This don't have any effect on the process, so we don't have any problems seen in our application center. So the perforation is don't have any side effects for the cladding.
And from side of the grinding process, Yannick?
For grinding, it is even an advantage if you have a perforated friction ring surface, because it improves the coolant of the contact zone.
Okay, so due to the time already, we are now at the end of our webinar. But as I mentioned already in the beginning, you are warmly welcome to send us your questions also directly to Dominic Grimminger, or you can also contact us by phone or whatever you want to do so, and we will collect all these questions and answer these questions in a very short period of time after this webinar. And again, you are warmly welcome to visit us on the Grinding Hub in Stuttgart and on our homepage, where you can find also other webinars which we did already in our market center. So thanks again that you joined us here during the webinar. It was our pleasure to present you our solutions from the turning process over the LMD process to the grinding process. Thanks again, and bye bye from my side.
Bye. Thank you.
Thank you very much for your attention.